Now, addition reactions. We are proceeding with addition reactions. So far, we have looked at halogenation as a type of addition reaction. We have looked at hydrogenation, and now we are looking at hydrohalogenation as a type of addition reaction. Now, hydrohalogenation refers to addition of hydrogen halides across the double bond. So let's take the same example. Now, hydrogen halides are compounds which are having hydrogen and halogen. Like for example, hydrogen iodide. It can be hydrogen fluoride, or it can be hydrogen bromide, or it can be hydrogen astatite, or even hydrogen fluoride. Any of these is an hydrogen halide. That is a compound of hydrogen and a member of group 7 of the periodic table. Are we together? So now, usually, addition reactions, not all hydrogen halides undergoes addition reactions. Those which are up in the periodic table usually do not undergo hydrohalogenation. Like for example, hydrogen fluoride does not react. This one does not react. But when you come to the next member, which is hydrogen fluoride, this one can react. Hydrogen bromide will also react. Hydrogen iodide will also react. And hydrogen astatite will also do what? React. Are we together? So now, the reaction increases as we move down. Are we together? So you have said the first one does not react. Okay? Hydrogen chloride, this one will react slowly. Okay? Slowly. This one, hydrogen bromide, will react moderately. Moderately. Okay? And then, hydrogen iodide, fast. Okay? Hydrogen astatite, very fast. You see that? So this one will be very fast. You can make the prediction. Very fast. So, as the size of the atom of the halogen, or as the size of the ion of the halogen increases, the rate of the reaction will also do what? Increase. So we are going to look at the following. Reaction with hydrogen iodide. Okay, so you have, this is ethyne, like this. This is ethyne. Okay, we are reacting with 2 moles of hydrogen iodide. Then we form the following product, which is carbon. Then here we have iodine. Here we have hydrogen. Here we have iodine. Here we have hydrogen. Here we have hydrogen. And here we have hydrogen. So this was ed. This was ed. Sorry, ethyne. Not edine, but ethyne. But the product here, this is carbon number 1 and this is carbon number 2. Then this one is going to be 1 diiodo ide. Diiodo ide. That is a very fast, I've just shown a summary. Now I want us to see the mechanism for that particular reaction. How does this reaction occur? So it will occur in 2 steps. Okay, so you have the first step, which is step 1. We have ethyne. This is our ethyne. Now you react with 1 mole of hydrogen iodide, like that. So in the same way the others were adding, this will also do the same. So hydrogen will add itself here, and then iodine will add itself there. So what will be the product? So the product is as follows. We had hydrogen, and then C, and then C, and then hydrogen. Then this carbon here, hydrogen has come. So here, iodine has come here. You write iodine, and then here, what do you write? Hydrogen. That is now 1 mole. Are we together? One mole of what? Hydrogen iodide, or one molecule of hydrogen iodide. Now let's look. The rule is what? Each carbon to be surrounded by 4 covalent bonds. So you have 1, 2, 3. One is remaining to reach 4. 1, 2, 3. One is remaining to reach how many? 4. So where do you put your double bond? In the middle there. Are you seeing that?
Yes.
So this was ethane. In step 1, we had ethane reacting with hydrogen iodide to give us, this is carbon number 1 and this is number 2. So this is either iodoethene or 1 iodoethene. Why 1? Because it is in carbon number 1. Usually, the carbon that has the branch or the substituent is the one that is given number 1, or the one which is very close to the the one which is having the substituent is our number 1. So that is 1 iodoethene. So in step 2, we'll begin with iodoethene. So you have C, double bond C. Okay. Let's do it here. C, double bond C. And then we have hydrogen, we have hydrogen, we have hydrogen, and we have iodine, like that. Is that okay? Now we are adding the second mole of what? Hydrogen iodide. So you have hydrogen iodide, like that. Now, this will follow a rule known as Markovnikov's rule. Markovnikov's rule. Okay. What does this rule say? Where we have more hydrogen is where the other hydrogen will come. Are we together? And where we have less hydrogen is where iodine will go. In other words, iodine is going where there is another iodine, and hydrogen is going to where we have more hydrogen. So it is a very simple rule, so don't look at the complex word. That's not an issue. So we take our hydrogen, it will come here because here we have 2 hydrogen. Are we together? And then this iodine will come here. Are you seeing that? Now what do you form? We now form this carbon. We had hydrogen here, carbon, hydrogen, carbon, and then carbon, and then hydrogen, and then hydrogen, and then iodine. On top here, iodine, and then on top here, hydrogen. Look at that. Now what's the name? This was what? 1 iodoethene. Or you can just say iodoethene. Iodoethene. In other words, in ethene, whichever carbon you place your iodine will become number 1. If you shift it from here to here, it is still what? 1 iodoethene. Are we together? So now we go to the last part, which is this one. We say the carbon that has the what? The substituent or the branch is number 1. So this is our number 1 and this is our number 2. Are we together? So this is going to be 1 for this substituent here, comma, 1 again for this other substituent here. So 1 for this iodine and 1 for this other iodine. Then you start with the prefix di, then iodo. Now we no longer have a double bond. We have single bonds alone. So this is going to be diiodoethane. It has changed from alkyne to, it has changed from alkyne to alkene, and then from alkene to alkane. As we continue carrying out hydrohalogenation, the bonds are being broken and new atoms are being introduced, leading to formation of an alkane from an what? An alkyne. Let us start there. The test for alkynes. The test for alkynes is the same as the test for alkenes, the same ones that we perform for alkenes. The only difference between alkynes and alkenes is that the reaction in alkynes is faster than in the case of alkenes. Are you together? So the first one is the decolorization tests. Okay? So the first one is that it decolorizes yellow chlorine water. So when an alkyne is present and then you bubble chlorine water through the what? You bubble the alkyne through the chlorine water. What will happen? It will become decolorized. Number two, it decolorizes brown bromine water. Okay? It decolorizes what? The brown bromine water. So when you bubble an alkyne, like for example ethyne, through the brown bromine water, what will happen? The color disappears, or it becomes decolorized. Number three is decolorization of the strong oxidizing agents. Are we together? So here we talk about decolorizes purple acidified potassium manganate 7. It decolorizes the purple acidified potassium manganate 7. Are we together? Very good. Lastly, it's not decolorization, but the change in color. Are we together? So it changes orange acidified potassium dichromate 6 to green. Are we together? How many tests have we mentioned? There are 3. First of all, decolorization of yellow chlorine water. Second one, decolorizes brown bromine water. The last one, decolorizes purple acidified potassium manganate 7. In other words, you are trying to get the color of the reagents. You must indicate the initial color and the final color. Then in this one, we have said changes. It changes of orange acidified potassium dichromate 6 to which color? To green. The color changes to which color? To green. From orange to green. So these are the tests. They are the same as the ones we performed for alkenes. The only difference is that these reactions proceed at a faster rate. Why are they proceeding at a faster rate as compared to alkenes? It is because of the presence of the carbon triple covalent bond. This functional group is weaker than the what? The carbon double covalent bond. So this is stronger bond as compared to this. So reactions in the case of alkynes will be faster than in the case of alkenes. That's the end of our lesson today.